Hello everyone. Okay, welcome to lecture 30. What we have been discussing since last two classes is the influence line diagram. In the first class of this week, we introduced the influence line diagram. Then in the second class, we did some examples and then learned how to draw influence line diagrams for different problems. Application of influence line diagram we will see definitely towards the end of this week. Now, but so far what we have done is when the load is just a concentrated load moving through the length of the beam, but now in most of the practical purposes, the load may not be just one single load. It may be distributed load, or it may be a train of concentrated load. So what we will do today is see how to deal with those distributed load. Okay. Now, so today's topic is this. You see, again consider the same problem. Now, in the previous example, it was just one concentrated load. They was moving through the length of the girder. Now, instead of that, now what we have a distributed load. Okay. Now we have two situations. One is, okay, let me show you the second situation. Now you see the difference between these two situations. Both are distributed loads. Now in the first case, we are concentrating on the central girder, right? In the first case, what happens is the length of the distributed load is more than the length of the girder. But in the second case, the length of the distributed force, this segment of distributed force, that is less than the length of the girder. Okay. What we will do now is we will consider this case a random length of not random, an arbitrary length of distributed load, and then see what happens when the load is less than the length of the girder and more than the length of the girder. And also we will see how the concept of influence line diagram can be used to find out the internal forces and support reactions for a given position of the distributed load, and also we will find out what will be the maximum, what will be the most critical position of this distributed load, so that the internal forces or support reactions in a structure is maximum. Okay. Now, but before that, quickly recap what we have learned so far. You see, if this is a beam, and we are interested in support reactions and the bending and shear force at C, at midpoint C. Now we know this is the influence line diagram for bending moment, and this ordinate is L by 4, and we also know that this is the influence line for shear force at C, and this is the influence line for reaction at A, and this is the influence line for reaction at B. So this we have already learned, right? Now, what is the application of this influence line? Now suppose if we have any concentrated load P1 at any arbitrary location. Okay. Now for that particular location, suppose these values are, this is y1, these ordinates we can compute from this influence line diagrams. And if we know that, then suppose define any general parameter psi, which could be moment at C, shear at C, reactions at Y and reaction B, depending on the context. Then psi can be written as P1 into Y1, right? Means P1 into this Y1 will give you the moment at C, P1 into this Y1 will give us moment at C, P1 into this Y1 reaction at A, and P1 into this Y1 will give us reaction at B. Okay. So this is the application of influence line diagram as far as we have a concentrated load. Okay. This we have learned so far, right? Now suppose it is not just one load. Suppose we have two load or three load, or say n I number of loads. It is a series of load. Okay. Now then what we have to do is we have to find out corresponding ordinates for say P2, then P3, and then corresponding ordinate for ith load. Okay. Then what will be the reactions or moment at C? Then this will be summation of Pi into Yi. Now, psi I is equal to, psi I could be anything of this from this depending on the context. Means if psi I is MC, then MC will be that P1 into this, P1 into Y1 plus P2 into this, and P3 into corresponding ordinate, similarly plus Pi into corresponding ordinate. These will give us moment. Similarly, if you have to find out shear force or support reactions, same concept can be applied. So, what we know is, we know that if we know the what we have done so far, we have the influence line diagram. Now, a structure, a beam, say for as of now we have demonstrated through beam only. So, let us take beam only. Now, then if you know the influence diagram for a beam, then what is the use of this influence diagram? If any load is applied at any location, then we need to compute, we need to find out the ordinate from the influence line diagram at that particular location and multiplied by the applied load. That will give us the corresponding internal forces or reactions. And if you have several such loads, then just the linear combination of this give us the total effect. Okay. So, now suppose this load is now replaced by, now it is just P1, P2 several concentrated load, right. Now, suppose they are replaced by, these concentrated loads are replaced by a distributed load like this. Okay. Now, remember one thing, whether the load is distributed or the load is concentrated or load is a train of concentrated load, influence line remains same. Influence, when we talk about influence line, it is just a one unit load, one unit concentrated load moving through the length of the beam. Okay. So, irrespective of the actual load, influence line is always drawn for unit concentrated load. Okay. So, now even the load is applied a distributed load, the influence line remains same, right. These are the influence line that remains same. What we are going to do here now is, in the previous slides we discussed that if we know the influence line, then for a series of concentrated load acting on the structure, how to get the internal forces and reactions. Now, what we are going to demonstrate here now is, now if we know the influence line diagram, then on that beam, if the beam is subjected to uniformly distributed load of given length, shorter than the length of the beam, then how to compute, how to use influence line diagrams to compute corresponding the support reactions and the internal forces. Okay. Now, so suppose this is at a your intensity of this distributed load is Q, and which is acting at a distance x1, right. Now, so load starts at x1 and ends here. Okay. Now, and suppose this distance is x2. Okay. So, load is between x1 and x2. x1 varies from 0 to L and x2 varies from 0 to L. Okay. When x1 is equal to 0, we will see, we putting x1 is equal to 0 and x2 is equal to L, it means the distributed load is on the entire structure. Okay. Now, suppose corresponding ordinate means at x1 and ordinate at x2 of the influence lines are as this. Okay. Okay, so this is at x1 and this is at x2, x1, x2, x1, x2, x1 and x2. Okay. Now, then suppose if we, then psi is again a general parameter, it could be moment at C, shear at C, or support reaction. Okay. Now, suppose what we have, when the loads were discrete concentrated load, then we use your summation sign. Okay. Now, instead of discrete load, it has a continuous load. So, summation will be replaced by an integration, isn't it? Now, integration of what? Integration of, if we take a small segment here with length dx, then on that segment these then on that segment the load will be q into dx. Okay. And suppose suppose corresponding ordinate here is y, then what will be psi? Psi will be that q dx into y and then integration between x1 to x2. Okay. It is the same expression, the previous expression when we have a discrete concentrated load, but since it is now continuous load, continuously distributed, continuously varying load, in this case this variation is constant uniform load. So, that summation has to be replaced by then integration sign, right, and then the limit of integration is from x1 to x2. Now, since at least for this case, if q is not constant, then you need to consider the variation of q here. For at least this problem, since q is constant, what we can do is we can take q outside of this. Now, if we take q outside of this, then what we are left with is integration of x1 x2 y into dx. Now, I believe you are familiar with this term. What is this? This gives you, this is essentially the area of these influence lines, of area of this between x1 of this diagram between x1 to x2, isn't it? So, essentially this is the area of this x1 to x2. So, then what happens? Then psi will be intensity of load multiplied by the corresponding area area in the influence line diagram. Okay. Now, this is the you find in the previous cases it was just a summation, and now in this case it is just you have the summation is replaced by integration. Okay. And final results that we are arrived at is if we need to find out, suppose a beam is subjected to uniformly distributed load, and now we need to find out what is the moment, shear or support reaction or any other internal forces at any particular location. What we need to find, what we can do is, we know the influence line diagrams. Influence line diagrams is depends on the structure, depends on their length, depends on their boundary condition. It does not depend on the what is the actual load on the structure. So, the influence line diagram remains same. We know the influence line diagram. Now, we need to find out what is the forces at a given location. Just place the we know the location of the uniformly distributed load. Now, the area of that diagram between the starting of the load and the end of the load will give you the corresponding internal forces. We will demonstrate through one example. Now, next is now this up to this it was very simple. Okay. Now, next is, you see, what we know now is, if you consider a beam which is subjected to some uniformly distributed load, and now before that, if you see, if the load is distributed load is over the entire span, then the entire influence line diagram will be the your internal forces. Okay. Now, what we have done so far is, we have a given beam which is subjected to a distributed load. We know the influence line diagram and find out, now using the influence line diagram we can determine what are the internal forces and support reactions, right. Now, now consider situation, we know that at the load changes its position, these internal forces and the internal forces support reaction, they also change. Now, naturally the question comes, what would be the most critical position, at what position of this distributed load your internal forces are maximum, and that is very important to know, because when you design a structure, you design for worst condition. So, what position of the load gives you that worst condition, that is important to know. What we will do next is, we will find out what would be the critical placement of a distributed load, so that bending moment at a given location is maximum. We will demonstrate that through again through a simply supported beam. Now, suppose a simply supported beam which is influence line diagrams, we know this is the influence line diagram. Just to make it general, it is, we have taken a very general dimension A and B. Now, suppose this is subjected to uniformly distributed load Q, and we do not really know the placing of this load, that we need to find out. Okay. Now, but what we know, this length of the distributed load is d. Okay. Now, suppose this distributed load is placed in such a way that C is the point where we need to find out the bending moment. Okay. Now, suppose the load is placed in such a way that the portion A1, the length A1 of this entire length is this side of C, and length B1 is this side of C. Means we can say that the point C divide the load in A1 A1 by B1 ratio. Okay. So, this part is this side and this part of this side. We still yet do not know what is the value of A1 and B1, how they depends on A and B, that we need to find out. Okay. Now, suppose this distance is the load is placed at a distance x from A. Okay. Now, this is the corresponding ordinate on the influence line diagram. Okay. And this distance is A1 and this distance is B1. Okay. Now, what is the problem? The problem is now, okay, now we can find out here. Now, the problem is, you see, this is the problem, that is the diagram that I showed you. Okay. What we need to find out, this load need to be, now this load can change its position. Okay. And if it changes position, accordingly A1 B1, the values of A1 B1 also changes. Okay. But A, B, they remain constant because they decide the location of C. Okay. Now, what we are interested is how this load to be placed such that the bending moment at C is maximum. Okay. Now, let us find out that. Now, suppose the load is placed in this way. Okay. Now, we need to find out what will be the value of A1 and B1 and how these values of A1, B1 related to AB, so that the position of this load can be uniquely determined, which gives us maximum bending moment at C. Okay. Okay, let us first draw the free body diagram for this position of this load. Let us draw the free body diagram of the entire structure. The free body diagram will be, this will be By, this will be By, this is By, and this is Ay. There will be Ax also, but since Ax is equal to 0, so not shown here. But please note that I am just to avoid drawing another same thing, I am showing the support reaction here itself, but when you actually show the support reaction with free body diagram, then the body has to be free. The support and the support reactions cannot be shown at the same place. This is a common mistake. Please be careful about this. So, this is the free body diagram. Okay. Now, once we know the free body diagram, let us find out the support reaction. Now, if we take moment about B, then what we get is Ay into L, Ay into this distance is L, L is equal to A plus B. Suppose L is equal to A plus B. So, total length is L. So, Ay into L, then minus. Now, what is this entire the load due to this entire this distributed this distribution, this will be Q into this distance. So, Q into D will be the load, Q into D will be the total load acting downward, and at what distance, the center of the distance, since it is distributed load, the center will be d by 2 from here. So, this value will be, you check, this total length is L, this distance is x. So, minus x, and from here it is d by 2, the centroid of this load. So, this is again minus d by 2. So, this is equal to 0, that is the this is actually MB is equal to 0. Okay. Now, this gives us AY is equal to QD into L minus X T by 2 divided by L. This is the support reaction. Okay. So it's a function of x. If the load changes position, so naturally support reaction will change, and this will change as per this. Again, you see this variation is linear variation. Okay. Now, let us take the free body diagram of this part AC. Okay, because we need to find out the bending moment at C. So let us take free body diagram of AC. So what would be the free body diagram of AC? This point is A and say this point is C. Okay. And what are the forces we have at A? We have the vertical reaction at AY, which already determined as this. Okay. Then we have shear force. This is VC, this is as per our sign convention, and then moment MC. Okay. Now, anything else? Yes, we have this distributed load also. This distributed load, which intensity is Q. Okay. And this distance is A. This distance is X. This distance is X. Okay. And this distance is A1. Okay. Now, let us now take summation of MC is equal to 0. Summation of MC is equal to 0. We need to find out what is the moment at C. Now, what are the forces that will contribute to this moment? The forces will be this AY, which will cause anti-clockwise moment, the MC itself, which is anti-clockwise, and the moment due to Q, which is anti-clockwise. Okay. Now, this give us, we can just draw a line here to separate. Okay. Now, this gives us what is the moment AY into A, which is clockwise, and then minus this force. What is this force? This is Q, and this distance, this is A, this is X. So, this distance is A minus X. So, force will be Q into A minus X, and what is at a distance? Distance again, it uniformly distributed load, half of A minus. So, A minus X by 2. Okay. This is the contribution from the distributed load, and then which is negative because it is anti-clockwise, and then minus MC, that is equal to 0. Okay. So, MC is again minus because it is anti-clockwise. Okay. Now, this gives us MC is equal to please is equal to QD L minus X minus D by 2 by L minus this part. This will be Q into A minus X whole square by 2. So, this is the expression for MC. Okay. What we want is that in this here, what defines the position of this unit load? Position of the unit load, position of this distributed load. The position of the distributed load is defined by this value x. Okay. Because if x changes, this position also changes. So, our problem was, if you remember, we want what would be the critical position of the load such that your moment at C is maximum. Okay. So, this has to be what would be the value of x for which the MC is maximum, and how we can determine that? We can determine this by dMC by dC is equal to 0, sorry, dmc by dx is equal to 0. So, let us do that. Now, if we have this, we have this expression just now we derived. Okay. Now, let us write this one. So, we take d mc dx is equal to 0, and if we do that, then what we have is qd, there will be a as well, you please correct, there will be a. Okay. So, because it is ay into a, ay is this into a. Now, this is q d a by q d a by L into minus 1 because it is minus x, and then minus q into a minus x, again minus 1 because of minus x, that is equal to 0, right. Now, if we have this, then we can determine what is the value of x, and this we get a minus x by d, please check that d is equal to a by L. Okay. Now, what is a minus x by d? Once you say that this is a minus x, a minus x is essentially a 1, that is how we defined, right. This is a 1. So, what we can write is here a 1 by d is equal to a by L. Okay. Now, what is a 1 by d? Okay. Now, this gives us a 1 by a is equal to d by L. Okay. Now, check here what is d? D is equal to a 1 plus b 1, right, and what is L? L is equal to a plus b. So, if we write here, this is equal to a 1 plus b 1 and L is equal to a plus b. So, this gives us a 1 by a is equal to b 1 by b, or finally a 1 by b 1 is equal to a by b. This is important. Okay. So, condition for this problem, condition for which the bending moment at C will be maximum is the load needs to be placed in such a way that this condition satisfied. What this condition says, that the point C divides this beam in A by B ratio. Now, what it says, that the ratio at which the point C divides the beam, the point C should divide the uniformly distributed this segment of this load at the same ratio. If it is done, then the bending moment at C will be maximum. Okay. Now, again, if you take any problem, we'll find out the problem is you place the uniformly to get the maximum bending moment at a particular location. First, what you need to do is draw the influence line diagram for the beam, and then you place the uniformly distributed load in such a way that this condition is satisfied. Once that placing is done, then rest is you take the area of the influence line diagram between those the starting and end point of the load to get the corresponding internal to get the bending moment at that particular location. Okay. So, that is all for uniformly distributed load. Now, you see there are many cases where you have you don't have uniformly, that cannot be idealized as uniformly distributed load, which are a train of concentrated load. Okay, the train of concentrated load is moving and the distance of this concentrated load is maintained. So, what we need to find out, what would be the position of this if we know the position of this concentrated load, then we can find out the corresponding internal forces. But now what problem is, we need to find out what would be the position of this strain of concentrated load for which the internal forces, for which the beam will be most critical. The same way, just now we have discussed what would be the position of distributed load for which the beam is most critical in bending. Okay, that's all for today. See you in the next class. Thank you.